Section 5.5, Power. Power is the rate of transforming energy or doing work. Let's think of an example. Imagine two fairly different people can lift the same mass, 50 kilograms, up to a certain height, the same height. They can both lift the same mass to the same height. Which of those two people is more powerful? Well, the answer depends on who can do it the fastest. Power is the rate of transforming energy or the rate of doing work. The equation for power is the net work divided by the elapsed time, or the change in energy over the elapsed time. Notice that power is a scalar quantity, and this is because both work and energy are scalar quantities. Since work and energy are measured in joules, and time is measured in seconds, 1 joule per second is equivalent to 1 watt. And the symbol for watts in physics is a capital letter W. Let's get straight to work with sample problem number 1. How much power does a swimmer produce if she transforms 2.4 kilojoules of chemical energy in food into kinetic and thermal energy in 12.5 seconds? So we know that power is equal to the change in energy over elapsed time, and she is burning through 2.4 kilojoules in 12.5 seconds. Now we have to convert kilojoules into joules, so that's 2.4 times 10 to the power of 3 joules divided by 12.5 seconds. If we punch this into our calculator to two significant digits, we get 190 joules per second. That's 190 watts of power. Therefore, the swimmer produces 190 watts of power. Let's try sample problem number 2. A 64 kilogram student climbs from the ground floor to the second floor of the school in 5.5 seconds. The second floor is 3.7 meters above the ground. What is the student's power? So power is equal to the change in energy divided by time. And in climbing to the second floor, the student has gained gravitational potential energy in that amount of time. And we can find how much gravitational potential energy using the equation mg delta h divided by delta t. You make that delta look more like a delta. There we go. And we can find the power generated in running up this flight of stairs, where the mass is 64 kilograms, G is 9.8 newtons per kilogram. The height is 3.7 meters. And all of this in 5.5 seconds. If we do so to two significant digits, we get 420 watts of power. Therefore, the student's power is 420 watts. All right. Now we're going to move a little bit to the discussion of energy ratings and the cost of using electricity. Companies that provide electrical energy to consumers use electricity meters to measure the total amount of electrical energy used. It's common for electricity meters to measure the electrical energy used in units of kilowatt hours. If we rearrange the equation, power equals change in energy over time, then we know that the energy used is equal to the power times time. Since power is measured in watts and time is measured in seconds, they actually use the kilowatt hour because the cost of electricity is actually small per second and much more measurable or more practical to measure it in hours and kilowatts. So a common use for energy in electricity is power times time. Now, different appliances use different amounts of energy, and their power rating is measured in watts. So here we have a laptop computer that uses 20 to 75 watts. A vacuum cleaner has a power rating of 200 to 700. All of these have different ratings. You can see some use more electricity, some use less electricity. Now, in order to calculate the cost of using these devices, we're going to, I'm going to draw you a little picture, and this little picture is the equation. So we're going to look at the different things that affect how much money you spend on electricity. And the first thing is the device itself. So different devices, as we mentioned in the table, use different amounts of electricity. So I'm drawing this plug to represent the different device that you can use. So cost depends on the device. It depends on for how long you use this device. So I'm drawing a little clock. It depends for how many days you use this device. And it depends on the power rating or the cost of using electricity that your electrical utility company charges you. When doing these, the electrical company will charge you in dollars per kilowatt hour. So it's important that we express this power rating in kilowatts. To go from watts to kilowatts, we divide by 1,000. Okay? We're going to measure our time in hours per day times the number of days we use the device or the appliance. So this becomes our equation. Cost is equal to the type of device times how long we use it for how many days and for the power rating that the electrical energy company gives you. So what is the cost of operating a 25-watt light bulb for 4 hours a day for 6 days if the price of electrical energy is 5 cents per kilowatt hour? First off, 25 watts divided by 1,000 equals 0.025 kilowatts. So the cost, if we use the equation above, it's funny that I call that an equation. It's just a bunch of pictures that were put together. They were put together because if you analyze the units, you'll see that all of these items cancel each other out. We did this came up with an equation by unit analysis, and you'll be left with dollars. Okay? Or whatever your unit of money is. So we'll punch these in. We have 0.025 kilowatts times 4 hours times 6 days, 4 hours per day, times 6 days, and the electric utility company charges you 5 cents per kilowatt hour, which in dollars is 0.05 per kilowatt hour. If you punch this together, you end up with $0.03 or 3 cents. Okay. You have some homework to do. plus Chapter 5 review questions. Do as many of them as you possibly can. Aim for 100%. It's the best way to be prepared. And do any corresponding LMS quizzes on this section. Good luck.